excess pressure inside a liquid flows. Due to surface tension, a drop or a bubble tends to contract, right? Due to surface tension, a drop or a bubble tends to contract. Contract means what? Reducing the size, right? So tends to contract. So it compresses the matter enclosed. Okay. So because of this, because when you reduce the size, what will happen? The matter inside will be compressed. Do you understand this? So compresses the matter enclosed. So when you compress the matter enclosed, what happens? There is an increase in the internal pressure. You understand this? Yes, in internal pressure. Okay, there is an increase in the internal pressure. So because of what, this prevents further contraction. So there is some pressure. So there is an equilibrium. On one side, it is compressing. On the other side, the matter inside will be agitating because yes, all these particles are being compressed and they get agitated. Is it not? They cannot withstand such type of enormous pressure. So what happens here? It tries to push up, right? So it prevents this pressure, take down this internal pressure prevents further contraction. Okay, prevents further contraction. Okay, further contraction. Do you understand this? Pardon? Contraction, because now the surface, let me consider a bubble like this or a sphere like this. Okay, the surface tension increases and they try to compress the matter inside. Are you able to follow? And because of the matter here encircled by this bubble, they try to repel each other and it prevents further shrinking of this size. And that is why an internal pressure is developed. And this increase in the pressure, what happens? Further contraction is prevented. Do you understand this? So internal pressure. Next. The there is now it has, I mean, it results in equilibrium. So in equilibrium, the pressure inside the bubble and the draw is greater than outside. You know very well the pressure inside. That is, this is the internal pressure I can put in. This is the external pressure. So the internal pressure is more than that of the external pressure because it has already compressed, and that is why it experiences some pressure. How this pressure is, exerted when there are more collision of molecules among themselves, there arises pressure. Do you understand? For example, in this room, I can accommodate 6 children or 8 children. More than that, if I admit what happened, it will be a chaos. Everybody will be trying to escape from this room or the classroom. Do you understand? If I accommodated 50 students, what will happen? Right? So the pressure inside will be definitely greater than that. This is based on number of molecules. Now let me have this room. Let me reduce the size of the room to half. And there also pressure increases. Do you agree with me? because of the shrinking of size. And that is why the internal pressure is greater than that of the external one. So there arises or there is a setup of equilibrium here. Do you understand? So the difference of pressure between these two sides of the liquid surface, okay, and that can be called the excess pressure, not external pressure, excess pressure. So what is this excess pressure? Take down. Excess pressure is equal to the difference between the internal pressure PIN minus, because PIN is greater than P external. Do you understand this? Okay. Now we are going to focus on this external pressure. How we can maintain this. So this excess, and that is why excess pressure is in. So excess pressure inside the liquid is equal to what? Internal pressure minus the external pressure. Or this external pressure is nothing but what? Both of them are Ex. Let me put out. So for your convenience, let me put O instead of. So Px can be, so let me rewrite. Px means excess pressure is equal to P inside pressure minus P outside pressure. This P outside pressure is nothing but the atmospheric pressure. Do you understand this? Got it? Okay. So schematically, let us draw a diagram here. For example, this was the original size of the bubble. Take the bigger circle, bigger sphere. Okay. Now you got the center, and now it has shrink the size because of the surface tension to this level. Are you able to follow? So what happens here? This R and this differential amount of R, we can put dr, a small decrease in size of the radius. And let me call it, this is the radius of the drop. Do you understand this? And now we have got the internal pressure. The internal pressure will be like this. Okay. So this is the internal pressure acting in this way. And there will be an external pressure here from the atmosphere. Are you able to follow? So the excess pressure is what? That is, so let me call it this one as PO, and this is PIN. Now we have arrived at P excess is equal to P in minus P out. That is Pi minus PO. So do you understand this basic idea? Now the initial surface, what is that? The initial surface of the surface area of the liquid drop, you can say. Okay, take down initial surface area. So let me call it the total surface area. Initially, I'll put I take down initial surface area. Initial total surface area. Being a drop, it is considered to be the spherical one. So 4 pi and r squared. R is the what? The radius of the drop here. So we should not get confused with the capillary. So I'm talking about the drop. Okay. Now final surface area. So final surface area means now here there is a decrease of dr. So I have to put dr. Okay. So this is the final surface. Okay. Without. So TSAI and TSA final. 4 by what about this? dr square. Do you understand this? The change in the volume. Okay. So dr square. D I r square. You can put dr square. Now the change, I mean the final surface area of the liquid drop. Okay. Take down the final surface area of the liquid drop means you can add these two. So TSA. Okay. TSA after adding. So this is the changing. This is the small change. I can put change. So now this is the final one. I can put 4 pi r square plus 4 pi dr square. Okay, why? Because look at the diagram here. So this is the 4 pi and the changed one is 4 pi dr square. So that's why I put plus r here. Okay. So the original r plus dr. I have to put the original r plus dr. Okay, this is the change and I have put here that is 4 pi, okay, of I have to put r plus dr whole square, not this one. 4 pi into r plus dr. Why r plus dr? Because the external sphere is r plus dr. So the total is r plus dr, capital R. You can put capital R. Do you understand? For this bigger rod or the cylinder, the sphere. Okay. Now let us split this here. 4 pi r and not 4 pi, 4 pi into, let us expand this. What is that? A plus b whole square formula. R square and dr square, dr square and 2r into dr. Do you understand this? Now let us expand. Multiply 4 pi r square plus 4 pi dr whole square plus and you have got this 2 into 4 pi 8 pi r into dr. Do you understand? Now this r is already small for a bubble. Okay. So if it is, the dr is very very small because it is a shrinkage size here. Okay. So let me call it a 0.05 and this is the dr. So when you are squaring on both sides, dr whole square means what? It is further reduced to what? Point not not then 25. It is reduced. So that is why it is negligible. Do you understand this? So since the dr squared is very very small, it is neglected. Take out. Since dr squared is very small, it is neglected. Right? Now let me take the remaining part and what are those here? 4 pi r squared. Okay, so this is the y. And then you have plus 8 pi r into d r. So do you understand this? Okay, got it. So what are the factors you have got? 4 pi into r squared is there. Okay, and then 8 pi r into dr. Okay. So this is the final pressure, final surface area. Got it? Now what we are going to study? We are going to study the difference in the surface area. Do you understand? So this is equation 1 and this is equation 2. Now we want to find out the difference here. So 2 minus 1. That gives you the difference in surface area, TSA. Do you understand this? So difference means increase here, increase in surface area, total surface area. So final surface area 4 pi r square plus 8 pi r into dr minus, you have got this final, initial 4 pi r square. So 4 pi r square. So you can cancel these two. So the result is the increase in TSA of the sphere is equal to what? That is 8 pi r d r. You understand? So this is the surface area. Remember, on which the surface tension is going to happen, right? And that is why the work done is equal to the external work, the external work, the external work done in increasing the total surface area of the drop. Okay, increasing the total surface area of the drop is equal to take out is equal to increase in surface energy, right? Increase in surface energy. So that is equal to, got it? That is equal to, that is, yes, increase in total surface area into surface tension. So it means the increase in surface area can be expressed by A pi and then what? R into VR into surface tension is represented by S. You got this point? Okay. So it means that is work done is equal to take down work done is equal to the excess pressure, okay, into area into change in radius. Change in radius. Are you able to follow? Okay. So this is one part. This is what the external work done. This is equation number three. According to this equation, let us arrive. So what is excess pressure? P into area 4 pi r square into change in radius means dr. Got it? So this is the work done. Got this point? So from this equation number 3 and 4, okay, from equation number 3 and 4, the LHS are equal, RHS should be equal. Okay. So in that case, P into, because work done is nothing but the energy associated with that. So P into 4 pi R squared into dr is equal to, what about this? 8 pi R dr into S. So shall we calculate? Now listen to me carefully. Dr can be cancelled and the 4 pi becomes 2 here. 4 pi, 8 pi means 2 here. Then what else I can strike out? R can be striked out. So this becomes R. Got it? Now the excess pressure is what? P is equal to, can you tell me what is the remaining 2s? So you can put 2s divided by R. That's all. Now can you tell me what is R here? So the radius of the bubble. Don't forget. What is that? The radius of the bubble, the sphere or drop, say. And what is S? S means what? The surface tension, right? And the P, that is nothing but the excess pressure. Okay. Now we can interpret in terms of pressure difference also. Okay. So this excess pressure is nothing but Pi, internal pressure, minus P, external pressure, Po. So that is equal to 2S divided by R. So this can be interpreted in this way also. And here you can replace by the atmospheric pressure. And this is the internal pressure. So from this you can easily calculate the internal pressure developed inside the sphere of a liquid, that is the bubble of the liquid. So we understand this concept. Okay. Now, but in the case of pressure inside the soap bubble, this is doubled because we have to consider two surface area, right? So in that case, we have to consider twice the area here. So two, and you can put now this is for excess pressure inside the soap bubble. Take that excess pressure inside Yes, so now let us work out here. And so this is the sphere the- before shrinking like this. And this is the internal pressure. You can put PI. And what about this? This is the out, outward pressure, PO, external pressure. Okay, out pressure, pressure outside. So increase in surface area of soap bubble. So here you need to consider twice of it. So you have to put because there are two surfaces. So 2 into 8 pi r and then dr. It means 16 pi r dr. Do you understand this concept? Okay. So similarly, you have to work out the external work. Okay. The external work done. The external work done in increasing the surface area of the soap bubble. Surface area of soap bubble. Are you able to follow? Is equal to the same logic. Increase in surface energy. Theta. Increase in surface energy. And this increase in surface energy is nothing but increase in surface area. Right? Into its surface tension. Are you able to follow? So that is equal to what is the increase in surface area that we already discussed? 16 pi r. So 16 pi r d r into this. So this is the external work done in soap bubble. So let me consider this as what the first equation. Okay. Now let us proceed. Have you noted down? Right. Next one. Now let us proceed with the work done. What is work done? Work done is here force into the change in radius, right? Force into displacement. In this case, the change in radius. So this force is equal to the excess pressure into area. Do you know why? Because we already know pressure is equal to extra pressure force by area. So that is why I have taken as this. So in that case, the excess pressure is nothing but P into what is the area? 4 pi r square. 4 pi r square. Okay. So 4 pi r square. No, no, no. Here we are talking about the only generally, simply speaking. So 4 pi r square. Okay. Surface area, the drop. No, that is the original one. Original surface area. Let me now, what is the work done here? Force W is equal to, you have this 4 rho into pi r, so you can put half. So, P into 4 pi r square into, that is the force. And the change in radius is this much. How much dr? Are you able to follow now? Okay, got it? Now we have two equations. In the previous, we have equation 1, that is, what is that? Um, this is 16. Yeah. Okay. So let us compare these two. So we have this two box are the two, wow, LHS are equal, so RHS must be equal. Therefore, P into 4 pi R square into dr is equal to, what was this equation? This is 16 pi. So 16 pi R dr into S. Okay, now let us strike out 4 pi here, 4. And then R square, and this is dr can be cancelled. Then this is R squared, this is R cancelled. Okay. Now in that case, what is our pressure inside the bubble? 4s divided by R. Okay. Are you able to follow? So this is the case with the soap bubble. Soap bubble. Now let us compare the original. What was the original one? 2s by R, the drop, normal liquid drop. But if it is a soap bubble, it is twice. So 2 into 2s, that is 4s by R. Is it clear now? Got it? So in terms of pressure, we can mention this as internal pressure minus outward pressure. That is the excess pressure is equal to, you can put 4s divided by R also. So you can interpret in this way also. So let me sum up. We have two types of heat pressure. One is normal drop, liquid drop. Another is a soap bubble. Okay. So normal drop and soap bubble. So what is P for this one? 2s by R. What about this? P is equal to 4s by. So don't forget this. Okay. Now listen to me. When air bubble of radius R lies at a depth h below the free surface. So you need to calculate that free surface of a liquid also of that particular density. So in that case, you have to include the that is a pressure which is responsible for the particular height, that is the depth inside the liquid. So in that case, pressure is equal to, as usual, 2s by R, and you have to include this pressure gradients also because of the depth. So H rho G. Are you able to follow? So in this case, the H indicates the depth. Being a bubble, for example, the surface level bubble and the bubble that is produced inside the liquid. In that case, what is the height of the bubble? That is depth of the bubble inside the liquid. That is also important. And this is the free space. For free space, you can call it 2s by R. But the bubble which is inside, deep inside the that is the content or the container, then in that case you have to include the pressure gradients also, that is H rho G. Okay. So here this is meant for the bubble inside the liquid. You understand this?